Okay, I'd like to solve some modulus equations. Some drawing the graphs does become useful. There's also a few techniques you need to be careful about, particularly when you're solving algebraically, being careful about which values of x are valid. And that's my caution to you, is you do have to check whether or not all the solutions you're finding are always valid. So this one I put up as being your starter, and hopefully most of you will quickly realise there are no solutions. The reason there are no solutions to this, if you recognise that, that means there's no solutions. The reason you hopefully will realise is when you do the modulus, this side must be greater than or equal to 0. This side is less than 0. So there's no way these two will overlap. There is no equality that can be had. Okay, so there are cases where there are no solutions. Okay, so we'll consider another example one. Let's say we've got 3x minus 1, and you could sketch the graph, and graphically you could find the solution to that being 5. How many solutions do you think there are originally? If it was 3x minus 1 is 5, you would find one solution. But remember, we've got a modulus function which can give us multiple values. So I'll just do a quick sketch of the graph to review what's going on. So we've got 3x minus 1, so it goes through minus 1. Let's say minus 1, goes up 3, goes up 3. So this is 2, 4, 6, 8. That's 8, minus 8, minus 8. So I'm using 1 square is 2 units from this graph. So we get the graph originally coming through, keeps going down, through there, through that one, and it keeps going. Now the point it bounces is going to be here. So this modulus point action happens when 3x minus 1 equals 0, says that x equals 1/3, and that's that point where it bounces. When it bounces, it then flips and goes back up the other way, and so should be going up and to there, into there. So those two should be actually copies of each other almost. So we've got a graph coming down like that, and it bounces up like so. And 5 would be a horizontal line. And remember, all equations are basically saying what's the intercept between 2 points. Okay. So you might be able to find them graphically if you do a really accurate drawing. How can we find it algebraically? That's, first of all, consider the x is not, the modulus isn't working. So modulus not working. And that is when x is greater than 1/3 or equal to. So that's everywhere on this portion of the graph over here. So that's the green bit. Okay, modulus isn't working. Now this is a domain that we are using. We've got to talk about domains and things, but we're specifying a domain where the modulus function doesn't work. If it's not working, it doesn't need to be written in, and that leads me to 3x minus 1 equals 5. Rearrange it, and hopefully you will all see x equals 2 is a solution. That one. Then we've got to consider the other possible spaces. So below that, we also have when x is less than 1/3. And that leads to, now everything inside this bracket is change sign. Because remember, that's the effect of what a modulus does. If it's above the threshold for this point, it's just that expression. If it's below that threshold, everything swaps round. So it equals 5, and we get things like minus 3x plus 1 is 5. Rearrange, we get 3x is minus 4, so x is minus 4 over 3. And hopefully we check, is this in the right area? Yes, it's in the correct domain. So that means that this is also a solution. Now you might want to check it, so we take our number and just do a quick check with it. 3 times minus 4 over 3 cancels to give us minus 4, subtract 1 is minus 5, and when you do the modulus of minus 5 we get 5. Yeah, that's fine. So we know it works. So that's one way you can actually check if the value is right. The other one is if you're very clear what values are working. You can you can give the answer using set notation. So x belongs to minus 4 over 3 and 2. And that's where those two numbers come from. So that's why this was slightly out. I think I've got the graph slightly out of place. So that's how we can get algebraically solve solutions. We consider where does the modulus happen. So I've got another example. I'm just going to whiz through some examples quite quickly. So we've got modulus x plus 2 equals 1 minus x. I'm not going to do it by drawing the graph, but we need to consider when x is greater than or equal to minus 2, and this is equal to 0. This side is fine, and that leads to the equation working. 1 minus x, rearrange, we get 2x equals minus 1, x equals minus a half, and that's inside my domain, it's fine. We also need to consider when x is less than 2. That leads to all of this changes sign. Oh, I missed out the x. Oh no, I didn't. So minus 2 is equal to 1 minus x. We bring our equations round, and we've got x goes over to that side, and I've got minus 1 equals 1 and nothing. That means there is no solution on that side of the graph. And if we check the graph, we have absolute on a lot of things is the way to calculate, put in the modulus. So absolute x plus 2, the left hand side, is parallel when the modulus kicks into this 1 minus x. So there is no solution on the left hand side, so we've only got the one solution there when x is a half. Okay, so come on to another question. I'm going to do a couple of fairly quick ones, and hopefully with one final one that will cover everything. I'm going to introduce two moduluses. We've got 3x minus 1 equals 1 plus modulus x. And now you need to think, when does each modulus affect the situation? So first of all, the threshold for this one, we think x equals a half is the kicker, which means that this is natural and in its normal form when x, so not a half, a third, so when x is greater than 1/3. Check this side, this one says it acts when x equals 0, greater than or equal to 0, greater than or equal to 1/3. So we now need combinations. When x is greater than 1/3 also satisfies that. So that's one region. We also need to think about what happens in the region between them. So we've got a line, we've got 0, we've got 1/3, and so far this first situation is this region on this side. Second one is when x is between 0 and 1/3. And this gives us our second region. And we've got our third region when x is less than 0. So let's look at region 1 of A, B, C. A, B and C. Actually A should be open as well because it keeps going. So let's consider region A. The domain is x is greater than or equal to 1/3. Neither of these are operating, so my equation is 3x minus 1 equals 1 plus, and this one doesn't need to operate either. Rearrange the equation, we get 2x equals 2, and we've got a solution when x equals 1. Is it in the correct domain? It is in the domain. So that's fine. Now consider the region between 0 and 1/3. Now, when we're less than 1/3, this modulus, first modulus, changes. So now we get the minus 3x minus 1, and that is equal to the right hand side, which works still, and that's working fine. Flip the signs, minus 3x plus 1 equals 1 plus x. Rearrange, so we get 4x on the right hand side and we get 0 on the left hand side. So this actually says that when x equals 0 we get a valid solution, and according to this, x equals 0, it is in the domain that we are looking for. And in the last region, when x is less than 0, both moduluses are doing their job, they're both flipping the sign. So we get minus 3x plus 1 is equal to 1, and now flipping the sign on the x, minus x. Rearrange them and we get 2x equals 0. So again, we get the answer when x equals 0. And that's sort of in domain or not. It depends how we defined our equals signs, but both of these agree on one solution. So copy the graph in. The blue one is the 1 plus modulus x, and the red one is modulus 3x minus 1. Our two solutions, when x equals 0 and when x equals 1. So we found them, and this is finding them by algebraic methods. Okay, so I've got one more I'd like to do. I was just trying to set the graph up for us. The last one we're trying to do is two functions are equal. I'd like to know what happens when 1 over x, when does it equal the modulus of x? And the reason I'm choosing this one is there is a little bit of a quirk in it as to what happens. So first of all, there isn't actually the key areas are when x is greater than or equal to 0, and when x is less than 0. That's when the two moduluses work. So this leads to the equation when it's greater, this is positive, so we get 1 over x equals x, which rearranges into 1 equals x squared, which tells me that there is two answers when x equals plus 1 and x equals minus 1. But we check our domain. And if you check the domain, we should find that x equals 1 is the only solution in that group. We don't consider the minus 1. When x is less than 0, let's see if we get some solutions. We've got 1 over x is equal to minus x now, because the modulus is working, and that leads us to minus 1 equals x squared. So we got x squared, negative sign, which means that we get x is equal to the square root of minus 1, and that is there are no real solutions. If you've ever seen this, this means that it's not a normal number. It's not a normal number from the number line. So x is not a member of our normal calculation, which effectively means for what we are dealing with, we can assume all our answers are in the domain for x must be a real number. There is no solution for that side of it. So my only solution will be when x equals 1. So let's have a quick look at it on the graph. So we've got solutions here, and the only solution is in that point there. This is the 1 over x function, and this is the modulus x function. If you ever want to use these, I think I've been hiding it from you. If you type in absolute x in GeoGebra and Desmos, that will tell you exactly where the solution, that will do the modulus. Okay, so there we are. That's functions that you can do solving equations, which now means that you should be able to try all the equations that are in 2a. In question 10, do have a look at it, be careful about what's happening, and I think that was it. Yeah.